Alright, hopefully just a quick video going over this domain and range investigation type thing, this in-class assignment, maybe it's called. But the directions should speak for itself about completing the tables and then using those tables to plot out the graph, like kind of an outline of the graph, hopefully even connecting the dots if you can, and then using all that all that stuff to help you come up with the domain and the range. But let's get rocking with this. So again, just kind of running through what you should be getting. Hopefully you've already tried this yourself. Maybe I should have mentioned that at the way start of this video a few seconds ago, but hopefully you're trying this first before watching the video to see what's what. But make sure you're plugging in negative numbers and you're being careful about squaring the entire, say like if you plug in -3, you're squaring the entire -3 to get +9 and then -2. So when you plot all these points, at least the ones that aren't out of bounds, you should get a parabola, which you should find that familiar. These quadratic equations or quadratic functions make parabolas. If you were to connect the dots, it would make that classic parabola U-shape. And then especially with the graph to help you, the domain is going to end up as all real numbers, which you're just going to have to write yourself. Like I'm not going to be able to write that in right now for you. But the domain is -infinity to +infinity. In other words, that's all real numbers. And one of the big ideas of this activity is to get you thinking about it like this. I know the table is here to help you and the graph is definitely going to help you, but if you're given an equation like this and you're asked about the domain, the whole thing that what I would focus on is this: what x values would you literally not be allowed to plug in for x? Like, is there any number that for some good reason you would not even be allowed to plug in for x? And with this equation, the answer is no. There's no reason why you can't plug in any number you want in for x. You're allowed to square any number that you can think of, any real number. So that's why the domain ends up being, by table and graph, all real numbers. And the range ends up being, especially if you look at the graph, from -2 to +infinity. And you kind of get that idea in the table. You definitely get that idea from looking at the graph, that it's everything that's greater than or equal to -2, in other words, -2 to infinity. But if you think about it, right, think of it this way. No matter what you plug in for x, you could plug in like -1,000,000 in for x. But when you square it, it's guaranteed to be 0 or positive. Like, in other words, the smallest x squared can ever be is 0. Remember, y is based on x squared minus 2. So the smallest that part can ever be is 0, and therefore when you put it all together, like x squared minus 2, I don't care what you're plugging in for x, the smallest answer for y you could ever get is -2. And that's why the range ends up what it is. For number 2, and again, I'm hoping you tried all this first, but the good news is for this video and stuff, and you getting a grip on all this, number 2 is going to be like the same exact sort of conversation. Let's see, -1 up, no, right 1 up 3, should be here. Those should be all the points that you're plotting, right? But look, again, for domain, Is there anything stopping you from plugging in anything you want for x? No. The domain is going to go left forever. So the domain, once again, is all real numbers, negative infinity to infinity. The range is going to be like 3 and up. So all y's that are greater than or equal to 3. In other words, 3 to infinity, 3 to positive infinity. And it's for the same reasons as number 1. I don't care what you're plugging in for x. Again, you could plug in positive 100, negative 100, it doesn't matter. Once you take the absolute value of whatever minus 1, this is going to be positive. I mean, 0 at the smallest, and then you're adding 3 for like a final y value, like a final answer for y. So the smallest this could ever be, no matter what you're plugging in for x, is 3, and that's why the range ends up the way it is. Okay, number 3 is definitely a lot trickier. Notice I'm adding a bunch of stuff here, but let's say you guys probably did, you plugged in 5 and you got that, and then you plugged in 4, and what should have happened was an error. If you try plugging in 4 for that x, you end up with 1 divided by 0, which does not exist. It's undefined. It's the only thing you're aware of in math right now that is indeterminate and doesn't make any sense, and it doesn't exist. So, yeah. But after that, because you can't divide by 0. I don't know if I said that. So when you plug in 3, you got that. When you plugged in 2, you got negative 1/2. So there's another point. There's another point. And I mean, not to talk about the domain a little too soon here, but I mean, one of the big punchlines of, number 3 is that, oh my gosh, like domain-wise, what can you not, like you literally are not allowed to plug in 4 for x. X would be allowed to be any number you could ever think of except 4. So the domain is going to be like x cannot equal 4. Or you could say, now listen carefully because I can't write this right now. You could say something like negative infinity to 4, and just put a parenthesis on 4, and then union that with 4 to positive infinity with another parenthesis on 4. So negative infinity to 4, and then 4 to infinity using all parentheses. Or you could say x is less than 4 or x is greater than 4. But essentially the domain is any number you want except 4, because if you try plugging in 4, you'd be dividing by 0. So on that note, I mean, maybe this is too early in the process here, but oh well. But maybe not. So there's going to be this thing called a vertical asymptote there, because the graph just doesn't exist for, there's not going to be a dot anywhere for x equals 4. The rest of the graph, I mean, the domain was like a big concern, but if I make some more dots, like 6, 0.5, 7 would be about 0.33. If the graph went all the way out to x equals 10, that's where the dot would be. But what's going on in here? Like, what about like 4.5? If I plugged in 4.5, I would end up with 2. If I plugged in like 4.3, I would end up with like negative 3 1/3. If I plugged in 4.1, it would be all the way up at 10. So imagine kind of what this graph is doing. And then what about like negative 6? And then what if I kept going to the left, like negative 6, negative 7, negative 8, negative 9, negative 10? Look at my y-coordinate for negative 10. Look at my y-coordinate for negative 100. So what is going on here? essentially this graph is, sorry, I messed up here. What's going on here? Like 3.5, negative 2. 3.8, negative 5. 3.9, like I can't plug in 4, like I literally can't plug in 4, but I could plug in 3.9 and get all the way down here at negative 10. So with all these extra dots that I've given you here going over this graph is going to have a curve right here that's just going to keep on getting closer and closer and closer and closer and closer to this vertical asymptote, but never touching it. And also, it's going to keep getting closer and closer and closer and closer and closer to the x-axis, but never, ever, ever touch it. Likewise over here, it's going to be another curve, but like sort of diagonally opposite of it. And it's going to keep creeping closer and closer and closer and closer, like 4.01, 4.0001, 4.00, you know what I mean? It's going to keep on getting closer and closer to the vertical asymptote, but never touch it. Likewise, look, 7, where's 7? 7, 8, 9, 10, if you plugged in 100, we would be getting smaller and smaller, but never hitting 0. And that's a big punchline here for the range. We're going to creep closer and closer and closer and closer to the x-axis over here as well, but never, ever, ever, what's this? Ooh, I had this prepared. Oh, just to make it all one color? Lame. Not necessary. But it is true. I mean, all these dots end up, so there's the graph, And it's a couple of curves that are diagonal of each other. And as far as the range goes, like, what can y never equal? No matter what you plug in for x, and by the way, you're just not allowed to plug in 4 for x, but anything else you plug in for x, no matter what you plug in for x, this entire fraction can never equal 0. 1 divided by whatever can never be, think about it. What can you divide 1 by for the whole thing to equal 0? Nothing. So that's why the range is kind of like the domain, except the range is that y can never equal 0. The tables sort of prove that. The graph sort of proves that. So the range is that the y can never equal 0. Alrighty? And then this one, I guess the big surprise here is that once you finish, actually never mind, because you're adding 2, so that's probably good, and that's probably good. But once we plug in negative 3, what happens? Negative 3 plus 2 is negative 1. So get those out of there. So like, what's the square root of negative 1? You start getting like errors on your calculator because it's imaginary, okay? It's an imaginary number, and those cannot be graphed on a real xy plane. Like these are only for real numbers in the xy plane, the Cartesian plane. So likewise, you try plugging in negative 4, error. You try plugging in negative 5, error. There is no graph over here for anything less than negative 2. There is no graph. You're literally not allowed, as far as like, as far as domains and stuff go, you are not allowed to let x equal anything that's less than negative 2, because you'd get like an imaginary answer. So in other words, this domain is any x greater than or equal to negative 2. Those are good. Anything greater than or equal to negative 2, like the graph is showing, because this is going to keep going. You can plug in 6, you can plug in 7, you can plug in 8. So it's from negative 2 to positive infinity is the domain. All right? The range, think about it. Like, what do you think is going on with the range? Just look at the graph. Doesn't it look like the range is from 0 to infinity? Because it is. And think about it. no matter what you plug in for x, can the square root of something ever be negative? No. So the fact that the graph ends up what it is and the range ends up what it is, 0 to infinity, makes sense if you look at, how square roots work. Once again, no matter what you plug in for x, y is going to equal this entire square root of whatever, and square root of things can never be negative. So that's why the range is like 0 to infinity. So in conclusion, because the biggest point of emphasis in these four, examples, it's probably domain. Like, if I had to pick the most important thing, is the domain. So in conclusion, domains get restricted not in situations like this. I mean, you can plug in whatever the heck you want for x, no problem. Once again, here, there's nothing stopping you from plugging in whatever you want for x. So two of the biggest situations that restrict your domain is denominators, because of, you're literally not allowed to be dividing by 0. So a denominator that has x in it, that'll restrict your domain a little bit. And the second biggest one, these are not the only two, but the other of the two biggest ones is square roots, because you can't take the square root of negative numbers when it comes to your domain. So those are the two big restrictions for now that on, domain. Okay?